Hello everyone, my name is Hidayat Shahid. I'm supervising your lab for Road Vehicle Dynamics course. In this video, I will walk you through what you need to do to complete your Lab 4 and Lab 5 exercise. The Lab 5 exercise simply is based on the same steps where the geometry will be modified. To just give you the context, you have already completed three experiments using flow-tech wind tunnel and scale models. This lab is associated with it's related to your lab 1 where you have done the experimental work associated with the rectangular prism as well as modified Ahmed's body. So in this lab exercise, I will show you the steps that you need to complete your lab 4. In terms of following the procedures, I will not be following the lab manual step by step because the intent of this video is to quickly show you how to set up the simulation, how to extract the results, and so on and so forth. So one thing I would emphasize, as it has been already emphasized in the lab manual, that to understand CFD, it requires a lot of time. You need to understand the numerical modeling, the type of solvers the commercial packages are using, and the assumptions, and so on and so forth. So it requires a lot of time if you really want to understand a proper way how to do the CFD modeling. Um, this lab is simply showing you the basic steps in SolidWorks, which has a very powerful um, flow simulation package, which can be used as a design tool. In the early design phases, you can quickly run the flow simulations and then change your design, and then you can perform detailed studies. So the steps that I'm showing you, I am going to not use high mesh density, which is critical for proper flow simulations, because it is understood that your computing power is limited. We have some machines in the lab that you can utilize as the number of elements in the flow simulation is going to increase, the computation requirement increase significantly. So and also, to keep this video short, I will be only showing you the steps. The accuracy of the flow simulations should not be taken as that these are accurate simulations, and that's what you're being taught in the lab anyway. So to make it short, I'm gonna get started with the exercise. To start the exercise, you can open SolidWorks and you can start with the new part. You start with the geometry modeling, which you have done it in many courses at Ontario Tech. So to start, the first thing I'm going to do is I'm going to change the units to mmgs. Once that's done, I'm going to save this file as, I am going to create a new folder in my, let's suppose I'm going to go into my documents. I'm going to create a new folder and I'm going to name this folder as lab 4. This way everything associated with this lab exercise, it will be saved in this folder, and I'm gonna call it lab 4. To start, I'm gonna start by modeling, creating sketch and do the 3D modeling using the basic steps in SolidWorks. I'm gonna select this top plane and I'm going to do a sketch. And for sketch, I'm going to select this center rectangle and I'm going to drag and drop, and I'm going to add some dimensions. In this side, I'm going to go, let's suppose 92. This one, I'm going to keep it as 10. And I'm going to go to Feature tab and I'm going to extrude this part, and I'm gonna use the mid-plane method, and I'm gonna specify here 70. I think this is what I have used in your lab manual. So as you can see, I have created this rectangular plate. I have the x direction is normal to this and y is pointing up and Z is pointing in this direction. So it's important when you're going to do the CFD simulation in SolidWorks that you understand where your global coordinates are, because this is where you need to specify your boundary conditions, flow parameters, and so on and so forth. So, and I'm gonna hit save, and I am almost ready to start the flow simulation. To get the flow simulation add-in, you need to click on the command manager. You can select the flow simulation from there, or also you can go to tools, tool add-ins. From here you can also select the flow simulation from there as well. Okay, so this is where it's selected. For example, I'm using 2021 version. So now the next step would be for me to start the simulation. So as soon as the flow simulation add-in is activated, this tab is there, and in here SolidWorks give you a wizard which you can follow to create your flow simulation study. So I'm going to start here. I'm going to by clicking on the wizard, it will prompt you to this dialog. In here you can add lab 4 for example, and the next thing is select this SI units and click on next. In here we are doing external flow because we will be modifying this geometry to match your geometry that you had used in your lab 1. So I'm just gonna exclude the cavities and so on and so forth. Gravity, that's what I'm interested in. As you can see in here, the gravity is in the negative direction. Its negative values default is 9.81 in Z component, but my global coordinate system, that's what I have emphasized in the lab manual as well, that I need to specify with respect to this Y, because the way I'm setting up my gravity should be applied with Y axis. So I'm just gonna set this one as 0, and here I'm gonna set this one as negative minus 9.81, and the next thing I'm gonna add my working fluid, and in the working fluid I'm gonna select air, and I'm gonna click on this add. SolidWorks provides the library where the properties are already in the database, but if you wanted to create your own fluid with your own properties, which is possible, you can create a custom a fluid as well. But for this lab we are just using air, so we're gonna click next. In here you specify the on the wall how things needs to be treated, the roughness and so on and so forth. For the purpose of this lab exercise we simply gonna leave this at 0, but if we are trying to modify for the proper simulation, we can measure the roughness of your test object that we tested in the lab. We can specify the roughness if needed, but for the purpose of this lab exercise we are not going to change this. The next thing is, in here I'm going to specify my velocity is along x-axis. So let's suppose I'm going to start with the 2 meters per second, and this is the parameter that you can change to create many studies to determine the flow characteristic at various speeds and so on and so forth. And I'm gonna hit finish. As soon as this is finished, so what basically SolidWorks does, it attaches this computational domain. On the left side you have this tab which is basically your flow manager. You can have a look at your project. All the study parameters there listed in here, and this is where you define various things when you are setting up your flow simulations, and also like other functions that you're used to in SolidWorks, the various there is more than one way to get to the tools that you need. So this computational domain is too big. You can modify it, and to simply how to modify it, you click on this computational domain. I'm just going to drag it here. You can grab this handle, you can position this differently, okay, and you can move and adjust things around. So when we are setting up the computational domain, you have to understand one thing. The bigger, the larger the computational domain, it's going to take longer time to solve the flow. So it's important that this computational domain is optimized in terms of the computational time and without jeopardizing the accuracy of your solution. So how do you figure this out? There are some standards. Steps can be used. There is white paper that we have provided you that you can look at, where the validation studies have been done on for various classical fluid mechanics problems. That helps you to identify the size of your computational domain, and also the mesh size. So for this case, how do you want to pick the computational domain? Ideally, you want to have the computational domain for this external flow situation such that along the boundaries of your computational domain, your flow should be uniform. And how do you come up with that? You have to do the far field boundary studies, where you vary your boundaries and then see if the parameters, the flow characteristics change. And you look at the flow field, you look at the pressure field, and that's how you come up with a good size for your computational domain. And the same thing you do with the mesh sizing and the grid study, which you will go through. So what I'm going to do is, you can also modify by right clicking on the computational domain. You can set the parameters in terms of uh, um, actual dimensions, and also this gives you a opportunity. You can also change from 3D simulation to 2D simulation, which you will do in one step, and compare the difference between the 3D simulation and 2D simulation. So for the here, I'm just gonna add some values here, 0.36, and on this side I'm gonna leave it to 0.1. On this side I'm gonna leave it to 1 as well. And for Z direction, I am simply gonna go 0.1. Sorry, this is Y, and Z I'm gonna go 0.1 and negative 0.1. So you can start with the different things. So as you can see, the computational domain is a lot smaller. And why do I want computational domain in this direction to be this much? This size I have just selected because we will be changing the length of this plate to match what you did in lab 1, and also will be changing the geometry as well. So I'm just gonna use this 0.36 because this is a reasonable length that I need to capture the flow on the backside. So you click OK, and your fluid domain is defined. You can save your file. This is always a good habit. And the next thing, what you're going to do is, in SolidWorks you can have goal defined, you can have equation goals, you can have the global goals and point goals and surface goals. It depends on the type of simulation that you're doing. If you're doing some thermal simulations, if you know the certain temperature conditions, certain flow parameters at various positions, and certain equations, for example drag force, that if you know for the say simple shapes, you can add those equations in there. But for the purpose of this video and lab exercise, I'm just going to leave everything there, and I'm simply only going to select this force X, and I'm going to click OK. And this is what you are supposed to do. So this appears here. So anything that you're doing will appear here. So in terms of mesh, that's the next step. We want to do the discretization of the computational domain. We're going to divide into smaller elements by adding various fluid cell and so on and so forth. You can change the parameters with the for your computational domain. And the way SolidWorks they have their own measure, and you can slide the how the grading. Sorry, I just gotta close this because I went really too much. So you can see how the grid changes. What you want to have near the walls more elements and so on and so forth, which you will go through a step by step in your lab manual. So for this quick simulation, I'm simply going to set this one to 4, for example, and I am going to click OK, and I am going to add, I'm simply going to create the mesh. So in here, if you have the machines, I have machines with 24 and 32 cores as well, but I'm just using my laptop for this simulation. This is why I don't want to create too many elements. So in here, I'm going to use all the cores on this machine, and I'm simply just creating the mesh around, and it just basically in this it has generated the mesh around, and it shows there is about 24,768 total cells, and about 336 cells are contacting the solids. This will need to be refined for the better simulations, but I want to run the simulation very quick so that the video doesn't become too long. So now I'm gonna hit save again. The next thing is simply solving this so we can hit the solver so that the calculations can be done. So now how to do it, you can simply right click, you can on lab 4 and you can run, and also you can right click there, you can run that study, or you can go here and do it. Alright, so I'm simply going to right click, run, and see what we get. It's running, so simply there will be an the solver is going to do the computation, is going to do the iterations till the force and the velocities and those everything gets reaches convergence, and this can take a long time depending on your mesh size. I have run the simulation with even about 5 million cells, and that takes a long time. And so the key is you need to have the optimization, how many elements that you want to use without jeopardizing the accuracy of your solution. What SolidWorks is using, if they're using one of their own solvers, there is some solver controls that one can use. I'm just gonna let it finish from here. As you can see, even with this not too many elements, is taking a little bit. So it says solver has finished, so let's view some of the results. For solve, you can have the calculation control. This is what I wanted to point while the solver was running, but it didn't let me to get in. So in here, you can specify the parameters that you need to use for the solution, and this is where you need to really understand what SolidWorks is using in the background as their solver. And the only way you can pick everything is when you spend quite a bit of time and understand how the solver, how it's modeling and how it's resolving various flow characteristics. So this is where you can modify and your solution parameters. So the solution has reached. I'm going to show you how to extract some results now. So in here, this result appears, and this is reading the files from the folder where you have saved. I am simply going to click on this lab 4. So this folder which has been created, this is where all the solution files are saved. And anytime you're creating something, if you're running the solution again, it will rewrite the files in here. Okay, so if the files are not loaded, you can unload the results, you can load the file. If you're opening the software again, you can simply go there and load the file from there. So now I already have some some plots that I can extract from here. So the first thing that I want to look at, I want to have some cut plots. To do so, you right click on this cut plot and you insert. And I am going to insert my cut plot on this front plane, and I want to see velocity x on that, for example. Okay, and I'm just going to change this parameter to 20, and I am selecting this contour plot, and I'm going to click OK. So this shows me the velocity profiles around for this simulation, and it helps me to identify where there are more velocity gradients, and then I can refine my parameters when I run my next study by refining the mesh size, and also I can change the computational domain if I am interested in certain parameters in certain places. You can also animate this, and by just simply right clicking on the plot which has been added, cut plot 1, you can rename and so on and so forth. I'm gonna hit plane. So as you can see, it's moving around the computational domain, and it shows you where your velocities are uniform, which is you have this legend here. So what you want to do is for your computational domain, you want to have the same velocity along this boundary and this boundary. Should be uniform if you're picking up if you're solving the solution with the good computational domain. So I'm just gonna stop animating this. Now I'm gonna simply hide this one by right clicking, hide, and the next thing I'm gonna look at the flow trajectories by right clicking on here, insert. What I am going to do is you can select the pattern. For example, if I select this face, and you can have, let's suppose I want to add 50 for this parameter in here, and I want to see what the velocity profile is. I'm going to click OK. So it's going to calculate. So it's basically providing how the flow is going from this face. So I'm going to hide this one. I'm going to add, insert another one, and in this case I'm going to select pattern on shape, and here I'm using this rectangle. So I want to determine how the flow is going, and let's suppose I change this to 50. There's a 3 options. You can specify line, sphere, and so on and so forth to visualize your flow. So I am simply clicking OK, and as you can see, it shows me the flow trajectories around the object, and I can animate this. Okay, so it shows how the flow is around, and in this region something is happening. I wanna look at that in a little bit more details. To do so, I'm going to stop this, and I can simply modify this, edit definition. I can just drag this one here because I want to see what's happening behind this plate. So I'm gonna click OK and play. I still did not pick up the details in the back, so I'm gonna add another definition. Right click, insert. What I am going to do is I am going to go here and I'm going to resize this. I'm going to bring it down, and I'm going to move this one up, and also I'm going to move this one, if possible, closer to the object so I can pick up the flow details in that region. And I'm going to go move a little bit here, and I'm going to add 50 and click OK. There you go. So you see I have picked up on this swirling flow in the back, so that helps me to understand what's happening behind there. And if I go animate this now, so as you can see, the flow comes in, it gets deflected, and then there's a backflow, these vortices in the back, and as you can see, it's pushing and it's basically pulling this object into this direction. So this will add the drag force in the back side, and also there's a drag force on the front side. So these are the things I won't go into details here, that will be covered in the lab session. So this is where the power of the software comes in. Even using not too many elements, we are able to pick up on the details and so on and so forth associated with these flow simulation. Now, if I did not want this backflow here, you can streamline your shape and then you can change the flow characteristics. When we are doing engineering analysis, we are always interested in some qualitative analysis, which would be looking at the flow and then trying to understand what's going on, and also the quantitative. For example, if you want to know what is the force on this face, how to extract that information, I'm going to show you how to do it. This is basically, you can do it by clicking on right clicking the surface parameter, insert. In here, let's suppose I am interested in the force on this, and I select this force, and I can simply hit show and it shows up in here. So this is the force due to the flow on this object at that speed. It's 0.015 newtons. And what if I want to pick up the combined force? I select this, I simply can go again and show. Okay, so as you can see, the force is increased. Now you can also export your data to Excel. You can generate the reports and so on and so forth for the studies and things like that. So as you can see, I have exported this to Excel, and then you can use it for your reports and so on and so forth. So not to make this video too long, I'm gonna now go and show you how to refine your mesh and so on and so forth, how to change the boundary, which computational domain I have already shown you. You just follow the same steps. So now I'm gonna show you how to clone this study and how we can compare our results. One thing we have to do is we have to do the mesh density study, which is changing the mesh size. We don't want our solutions to be dependent on the mesh. We want them to be independent of mesh size to be reliable. The key in CFD is you need to start with the simple models, then do the validating studies and build your confidence, understand what the software is doing. It doesn't matter which software you use, and then you start building your models step by step, and don't just simply jump in and run a solution without understanding anything, and then it's simply garbage in, garbage out. So what I'm gonna do is I'm gonna save this, and you can hide everything, hide all. So, and I'm gonna hide my force here as well. Now I'm gonna show you how to clone this study, because we want to run this study next one. For example, I want to change the mesh size, I want to have more refinement around this object, I may want to change my computational domain, or I may want to change my flow parameters. I want to run the simulation at higher speed, for example. Let's see what happens. The first thing I'm going to do is in here, I am going to, how you can do is you simply go to this project tree, you right click, and then you clone this project, and then simply change this one with some description. For example, I want to run this same case with the higher speed. Let's suppose I want to run at 20 meters per second. That's what I am going to name it. Okay, it's invalid, it's not allowing me, so basically I'm going to remove this slash from there. So here is now this project has been, everything is copied. The only thing, there are no results because we have not gotten, we didn't do the solution yet, but all the parameters are set here, and this is activated. So now I want to run this one as 20 meters per second, for example. How to do it? You can simply go to in here, right click on this input data, and you select general settings. So the setup that we did initially using the wizard, all those parameters are saved here. So in here I had these initial and ambient conditions. I am going to simply change this velocity to 20 meters per second, apply, and OK. And the next thing, if I'm not changing anything else, I can simply solve this. And whenever you're solving, try to, if you're building on this previous simulation and you have not changed things, but this study has been cloned, if we were changing some parameters within the same study, you could start new calculation, but you can use the previous results. It speeds up the convergence in many cases. So I'm simply going to run and wait for the solution to achieve. Let's wait. Again, we haven't changed the fluid cell and anything, and I'm gonna show you how to do that once this solution is done. It should be a couple of minutes more. And the solution time, it depends on the computational power that you have on your machine, and how many processes you're running, how many cores you have, the CPU, and so on and so forth. All right. Let's see what we get. I expect the drag force that we had measured, it will change, should change significantly because we have increased the flow speed. So as you can see, it may take more iterations for the high flow. Because of the low flow, it went pretty quick. And the mesh size, even you determine one mesh size is okay for the laminar flow, it may not be okay in the if the you have turbulent flow and so on and so forth. So it's always, you have to make engineering judgment and do the analysis properly. So now the solution is reached and results are loaded, and there will be a new folder created in the same folder directory where your this simulation results are saved. Let's suppose if I just simply want to show these flow trajectories. So here we go. So as you can see, the flow is similar. In this case, I'm gonna stop here. I just wanna you can explore other things that I have already covered. I just want to show this surface parameters, which was the force. As you can see, it has it's now 2.119 newtons compared to the previous one. So this is only thing that we have changed is the flow speed. So this is the direct result of that. So I'm gonna hide this. Now I'm gonna show you how you can refine your mesh, and that's what I am going to show you in this step. So now we have done this. I want to do another study to see if my results change if I change my mesh size. So how you can do it, you can simply edit definition by sliding this initial mesh. You can do it there, but you will be ending up adding all the elements in the entire computational domain. What I want is I want the local refinement, and how you can do that is simply right clicking, insert local mesh. In here you select this region, and I am going to use a cuboid. It also gives you cylinder and so on and so forth. What I want to do is I want to pick up more flow details close. I am going to create this box around, and I am going to refine my cells, and I'm not going to do too many here because it will take a long time for it to generate the mesh. So I'm just simply going to click OK, and if I am going to do this study and I want it to be accurate and reliable, I will be creating a lot more cells near the object. Then it will have another cuboid around it with a little bit less detailed, less elements, and then I will have another body around it, and that's how I will simply specify my mesh. So in here this local mesh has been created, and if I go right click and create the mesh, I'm simply only creating the mesh in this case. I'm not changing anything other than that. So as you can see, the total elements have increased. So if I'm gonna get a solution for this one, it's gonna take a longer time, which I won't do it because otherwise the video becomes too long. So and I am going to add another refinement. I'm simply going to edit this mesh refinement, and I'm gonna change this to 1 and I'm gonna change this to 2, let's suppose. And now let's put the create the mesh again. So as you can see, the total cells are now increased to almost 200,000. So my computational time will be a lot higher in this case. So it will take long time to do to run the simulation if I use the same computer. So in the lab manual, you're asked to also run the analysis with the 2 dimension. Now I'm going to show you how to do it, because that will run very quickly. So to do that, I'm simply going to save this. I'm going to right click in here, and I'm going to clone this, and I'm going to make this one as 2D. Okay, and I'm gonna click alright. In that case, what we are doing is we're just running in the analysis in the 2-dimensional. With the 2-dimensional analysis, what will happen is you will miss on these end effects, and you always have to do the it's a trade-off. How fast simulation you want, how much accuracy is required, and can you is 2D analysis good enough for the problem that you're working on. It has to be investigated, it has to be assessed properly. So now in here, this is activated now. So how to convert this into 2-dimensional simulation is simply you right click on this computational domain, add a definition, select this 2D. So basically what's doing is it's going to do the simulation within this region, and your computational domain is changed. So in this case, I don't need, I'm just going to move this one around. So the computational domain is always um, adjusted by SOLIDWORKS automatically whenever you make any change to the geometry, any change to the type of analysis that you're running, 3D or 2D. I'm just going to run it with this setting, for example. So now, as you can see, it is basically focused on in that region only. So if I create my mesh here, let's see how many elements will be included in my computational domain. So you see it's 12,000 compared to 200,000, but we are missing on the end effects. I'm going to run this one because it will be very quick. So I am going to run this and show you the differences that you are supposed to be looking at during your lab exercise. And I have done some simulations, like, with the 5 million cells for the same problem. It took about a day on a better machine, so it depends. Alright, solver is finished. Now let's look at some of the characteristics that we have been looking at. As you can see, new folder with the 3.fd will be created in your working directory, so it's important to create a folder so that nothing is rewritten. And if we look at the flow trajectories, so this is what's picking up. Okay, so I can change, and I know there is another vertex there. I can change my definitions. Okay, and I need to modify that. Stop. Okay. In this case, I just want to change my definition of the velocity profiles, how I am extracting this. Okay, and I'm gonna move it a little bit. So as you can see, by moving this, I know there's a vertex there. I can pick that up by looking at the flow. So whenever you're doing flow simulation, you need to really assess what the software is showing you. It's basically showing you how you're setting up what you're looking at. So the internal flow and stuff, we have the same structure in here. Because of gravity, this flow is a little bit shifted downwards. So it is calculating things, but you can compare surface parameters. For example, if I show here, this is 0.723 newtons because the area is different, so you can scale it up to see if the forces are the same, and the scaling has to be done with respect to the area which is used to compute this, and also the area of the overall shape when we did the 3D simulation. So um, I'm gonna hide this, and I'm going to do this show this cut plot. So you can see the flow characteristics it's picking up, but it is more or less similar. But the computational domain, because I changed the size, so there's a deviation. So if I need to run this simulation with the better solution, I will need to extend this boundary in this way. I will extend it in this direction. I will extend it in this direction. So now I'm going to show you the next step that will be needed for your lab 5. In the lab 5, we're going to change the geometry. I'm going to save this, and to change the geometry, simply I am going to copy this in a new folder, and I'm gonna save this one as, for example, I'm gonna create a new folder, lab 5, and I'm gonna call this one lab 5A, for example. So you can change use the names as appropriate. Lab 5A, for example, and I'm gonna hide all these plots. And what I'm gonna do is I'm gonna make the change with this three-dimensional study that I did. I just double click there. I wanna make the change to this geometry. And how to do it? I'm simply going to this feature manager, and all I am going to do is I'm going to change this dimension. For example, I am going to change it to let's suppose 92 in this one. Okay, and as soon as I change the geometry, it says, do you want to reset the computational domain? I can say yes or no. I'm simply going to say yes, and I will modify this domain anyway. And then the sketch, edit, okay, and I'm going to change for example, this dimension to 180, and this dimension is 92. I'm gonna leave this one as 92. Okay, and exit. And this one, just double check the dimensions in your lab manual, which you will see on Canvas. I am going to change this one to 60 to match what you had tested in lab 1. I am just doing on top of my head. I'm not specifying the exact dimensions that may be needed. So as you can see, now this resembles what you tested in your lab 1. The only thing that's missing is the floor of the wind tunnel, which we will add. Okay, so if you were to run the analysis on this, the thing is you will need to go to this simply here. One thing you can do is you can delete this project, for example. From here you can delete this project, and then you can clone from this. Okay, and to activate this, you double click, so this appears. So the computational domain, edit definition, you can change it the same way we did in the other the previously, and then you run the simulations by changing your specifying your the mesh and so on and so forth. In this case, if I click on this, so the mesh is defined here. It's not I will need to go and edit definition for this one. For example, if I go across here, and I go across here and click OK, and if I right click here I can add and create the mesh and see how many elements we have in this case. So 285, because I am increasing my refinement zone. It will take a little bit longer to run this simulation. So what I'm going to do is to just quickly run it. I am going to delete my local mesh, and I am going to create mesh with the small number of um, cells, so that I can quickly show you something here. And I'm going to change my computational domain here. I am going to move closer here. I'm going to move closer on this side and click OK. And I am going to create mesh again, because I always like to see how many elements I'm using before I start solving. So now let's run the simulation again. Right click, run. And in next few minutes I will end this video so that it's not way too long. In this case, what you will notice, there will be more backflows on the side, top, and on the bottom, which can change the characteristics associated with the external flow. So solve result. So let's now have a look at the results, for example. Okay. Let's look at the surface plot. Show surface parameter. So you can see the drag force is different on the front and on the back. And if I go at change the definition, if I include these surfaces, the total force, if I show, it is 1.36. The overall magnitude on these surfaces is a lot less compared to the back and the front. So that's one thing that you have to analyze as a part of the lab exercise, and then come up with some explanation, which I won't explain here. Now let's look at the flow trajectories. So you can see you have the same swirling flow, but if I am looking at this simulation, I need more space, more larger computational domain in the back. I need larger on here because I'm missing on something, because there are some flows happening on the side, and also I need the mesh refinement right away. By looking at the flow characteristics, I know that this needs to be revised. So this is the exercise that you're going through in this lab 5. So I am going to just stop this one here, and the next step that you will be going to do in the lab exercise is refining your model, running at the wind speeds that you used in your lab 1, and then compare with the data that you got, and see how close you get. And if it's not close, you need to describe what's happening. Is your modeling correct? Is the computational domain? Are there the surface roughnesses and other factors? Are there issues with the overall modeling, and so on and so forth? But to match completely your lab 1, you will be modifying this geometry and convert this into the Ahmed's body, which you tested, and then you will see how the flow changes, how the drag forces change by streamlining, and so on and so forth. And another thing that you will do is you will add the surface close to the bottom, the exactly way we place the model in the wind tunnel. we will have the surface attached here and the column that was used to connect with the triple beam. So I will stop this video here. I hope this is helpful and easy way you to get started. Please follow your lab manual, and if there are any questions, please talk to your TA. Thank you.